Okay, so we're talking about acids and bases. Properties and acids of acids and bases is the first inquiry question for Module 6. Module 6, the whole thing is about acids and bases, and how it's kind of structured is you start off talking about what is an acid, what is a base, what are the different theories behind it. Then you get to the next inquiry question, which is using Brønsted-Lowry theory, and that's when you just hone in onto one theory about acids and bases and just talk a lot about that, do calculations that relate to that specific theory, and then you use that to do quantitative analysis, which is your titration questions. Now, something to keep in mind for all of Module 6 is, in my opinion, it's very similar to Module 5 in terms of the skills that you have to use. So there's a good amount of theory at the start, like there is in Module 5 with LCP and whatever, but towards the end it gets really calculation based. And for both Module 5 equilibrium questions, where you have the ICE table and all that, both those types of calculations and titration calculations have a massive focus on moles, and moles are so important in getting the correct answer. So if you're not very good at balancing equations, if you're not very good at paying attention to the molar ratios, now is a really good time to get brushing up on that, because Module 6 titration questions almost completely relies on your ability to keep track of your molar ratios. But we'll get to that later. We're starting off strong with simple acids versus bases. So acids, they have a pH under 7. 7 is neutral. Anything under is acidic. The more acidic, the lower. Then you have the sour taste. So if you think of like lemons, they're acidic, they taste sour. And they feel corrosive, which is why you take a lot of safety precautions in the lab when you use high concentrations of acids, because you don't want to get yourself acid burn. For the nomenclature, oh, that's another thing. I just completely skipped that thing in green. They usually contain a hydrogen ion. So a hydrogen ion plus an anion of sorts. Sometimes it's a polyatomic anion, sometimes it's just a normal anion. Yeah. But for hydrohalic acids, which are the ones that you've probably heard of before, like hydrochloric acid, hydrofluoric acid, just like I was saying just then, you have hydro, and then you put the name of the element there. So fluoride becomes fluoric, hydrofluoric, and then you say acid at the end, hydrofluoric acid, hydrochloric acid. And then the formula for that would just be like HF, HCl, HBr. Very simple. For polyatomic ions, it depends on whether it's an 8 ion or an 8 ion. So your 8 ions are probably the ones that you've memorized. So phosphate, carbonate, sulfate, nitrate. They become phosphoric, carbonic, nitric, sulfuric acid. That's what they become. You add ic at the end and then acid. Those are your 8 ions. Your 8 ions, you're probably not as familiar with, but 8 ions are your 8 ions minus 1 oxygen. So nitrite is nitrate minus 1 oxygen. So instead of NO3, it's NO2. So that's how you do a nitrate to nitrite, carbonate to carbonite. And for those, instead of having ite, you add us on the end. So phosphorus acid, nitrous acid. So that's how you name those. Bases, pretty much the opposite of acids. We have a pH that's over 7. We have a bitter taste instead of a sour taste, and they feel a bit slippery, feel a bit caustic. And most of the time they are a cation plus a hydroxide. Now, don't go mistaking this for like all bases have a hydroxide, because that's not the case. You can see in this slide with the nomenclature, there's sodium carbonate and bicarbonate, which they aren't hydroxides, but they're still bases. So don't go thinking that every single base is a metal hydroxide, because it's not. But most of them are. Most of the ones that you'll come across in any sort of HSC question will be hydroxide. So you just name them as you normally would. You just go sodium hydroxide or potassium hydroxide. You just add it on. So bases are really easy to name. Next thing on this inquiry question, like dot point, is indicators. So indicators, as the name suggests, they indicate the pH. It's usually a solution that varies in color, and the different colors can tell us the different pHs. It's often an inorganic acid that's really weak, and this means that they exist at an equilibrium, because weak acids exist at equilibrium. So it means that we just learned about equilibrium, did a little recap, but basically when you add an acid, it will affect one side and cause it to shift to one color specifically, and that color will tell us, oh, it's an acid. Then if you add a base, it'll shift the opposite direction and it will change a different color, and then it will tell us that's a base. So that's how indicators work. If you add an indicator to a solution of unknown pH, it'll usually tell you a range of pHs that it could be in, and that can give some indication as to if it's acidic, basic, what the number of pH is. A common one that you might have used before is litmus paper. You have red litmus paper and you have blue litmus paper. Red is for acid, blue is for base. So you remember that because base and blue not sound the same. They start with the same letter. Base and blue start with the same letter, which means that they go together. So if you have blue litmus paper and you put it in a base, it should not change colors. Whereas if you have red litmus paper and you put it in a base, it should change to blue. Similarly, you have an acid and red. They both end in D, so you know they go together. But if you have red litmus paper and you chuck it into an acid, then it shouldn't change color. It should stay red. But if you have red litmus paper and you chuck it into a base, it should turn blue. Oh, and if you have blue litmus paper and you chuck it into an acid, it should change red. So that's how litmus paper works. Should go the color that it matches. So like acid should turn red, bases should turn blue. Other indicators are ones that you can like drop in and then it will change the color of the solution. Obviously with this type of indicator, there are some positives and some negatives. If you have a solution that's quite opaque or very colored, it can be very difficult to see any color changes in indicators, and it might skew the way you read the pH. But in general, these are really good to test pH. Especially like they're good to test ranges of pH, because if you look, let's look at phenolphthalein, which is the clear to pink one. This is the one you use for titrations most of the time, and it's really fun. It turns a pretty little pink color, but it's clear for so long and then it immediately turns pink. So it's not really a range where you can see exactly what pH it is, because if it's clear, you don't know whether you're at a pH of 1, which is super acidic, or if you're at a pH of like 7, which is neutral. You don't know because all of it looks clear. So that's a kind of downfall of indicators. But the main ones that you'll hear a lot about are methyl orange, bromothymol blue, phenolphthalein, and litmus. Now, if we compare methyl orange, bromothymol blue, and phenolphthalein, what you'll notice is that the change in color, like the massive change in color, so from red to yellow, from yellow to blue, and from clear to pink, those changes in colors happen at different points in the spectrum of pH. So methyl orange, it happens kind of early. It happens before we hit neutral. The change in color happens when it's still acidic. And in phenolphthalein, the change in color happens when it's basic. It's far on the right. Whereas bromothymol blue, it's right in the middle. So those indicators will be used for different things, different titrations, because different endpoints. But we'll talk about that later because that probably doesn't make sense right now. You can make an indicator from red cabbage. It's a really fun prac. We did it in class. You chop cabbage, you boil it, and then you cool it, and then it's an indicator. How does this work? You can read there. I don't know how it works. Sorry, that was a yawn. I don't really know exactly how it works, but I know the colors. And it's red to yellow. It goes through this really nice spectrum of colors, and it's very similar color spectrum as universal indicator. So universal indicator is a mix of a ton of different indicators to make this one massive rainbow spectrum. We start with red, like a deep red, is super acidic. Then green is neutral, and then deep blue is basic. So litmus probably has something to do with it if red is acidic and blue is basic. But yeah, indicators are really interesting. Universal indicator is probably the one to use if you want a specific number of pH, because you can see that like 3 and 4 are yellow, whereas 1 and 2 are red. So you'll be able to tell the strength, like the acids apart, and the bases apart. So that's good. The last kind of thing that you have to do in the first inquiry question of Module 6 are acid reactions. So you should have done this at some point in your chemistry career already, but we talk about it again because it's important. Acids. Acids can react with bases, which are, this is like the main reaction that you need to know for the HSC, neutralization reactions. So you have the acid plus base equals salt, water, and heat. That heat just means that it's an exothermic reaction. Neutralization is always exothermic, so that's why heat is there. Then some examples of that are your standard hydrochloric acid, so HCl, plus sodium hydroxide, which is NaOH, makes water, and then sodium chloride, which is the salt. And then obviously heat, but it's not written there. Cool. Then you've got acid carbonate reactions. Acid carbonate reactions are cool. They form little gas bubbles. And it's just an acid plus carbonate equals salt, water, and carbon dioxide gas. So very similar to a base, but this time we get bubbles of carbon dioxide gas. Then we have acid metal reactions. Acid plus a metal makes salt and hydrogen gas. Same thing, have bubbles from the gas, so that's an indicator of the reaction. But yeah, those are the 3 main acid reactions you need to know. The biggest and most important one, though, is acids plus bases makes salt plus water, and then heat. You just got to know that it's exothermic. And if you know that, you are good to start on titrations. Like if you know how to write out a neutralization reaction, you're probably good to do titrations. But more about neutralization. You actually use neutralization quite regularly. You're just not aware of it. So drinking water is treated to be neutral. From where water comes from, if you think about it, drinking water usually comes from not a plant, but like from a place where it's not going to be pure water straight away. They clean it. They want it to be neutral. They have different chemicals added in so that it's neutralized and then good for drinking. So whenever you drink water from the tap, just know that that's undergone a neutralization reaction. Chemical spills are also a big one. Chemical spills, if we have a massive spill of acid, we don't want that just going out, because like acid is, as we said before, corrosive. You don't want acid just lying around in massive spills where it can be a risk, so you neutralize it. And the main way they do it is with sodium bicarbonate. It's just a powdered substance. You just sprinkle it everywhere and it will neutralize the acid or the base. That's a great thing about sodium bicarbonate, because it's amphiprotic. So if you don't know whether it's an acid or a base that you've built, you just chuck on sodium bicarbonate and it will clean up your mess. Even if it's an acid, even if it's a base, it doesn't care because it's amphiprotic. Talk about that more later. And then also like antacids, they neutralize stomach acid to make you feel better in the stomach. That's just how the medicine works. Also with like bee stings, sometimes you put sometimes with different stings there's bases involved, so you put vinegar for the acid because vinegar is acetic acid. There's just a bunch of different ways that neutralization comes in handy in the everyday that we just don't appreciate that much, but neutralization is so important. So start appreciating neutralization. As I said before, neutralization is always exothermic, and that's because when it comes down to the net reaction, it's just H3O plus OH, so hydronium plus hydroxide, makes water. And since that net reaction is really all that's happening in every single neutralization reaction. So since they're all the same, they all have the same enthalpy, which is about -57, and therefore it's always exothermic. So there's that. Final thing before we get on to the second inquiry question, which I think is very important, is our good friends Lavoisier, Davy, Arrhenius, and Brønsted-Lowry. These are the 4 theories that you are required to know about acids and bases. Acid-base theory is quite interesting, I think. It's really easy to remember, in my opinion, because I think there's such a natural progression between the different theories. It's like, it makes sense, the order, so it's not too hard. But obviously it's still theory, and theory kind of sucks to memorize. But if you understand it, you don't need to memorize it because it's all just embedded in your head. But first theory is Lavoisier. I don't know if I'm saying that correctly. Doesn't matter. But it just showed that lots of non-metal compounds and oxygen, they produce acids when dissolved in water. So carbon dioxide, when dissolved in water, produced an acid. And the hypothesis then was that the oxygen is what's causing the compounds to become acidic in water. Why did this happen? Why did he think that? He just noticed it. But why did we abandon that theory? It's because metal oxides form basic solutions, and it didn't explain why things like hydrochloric acid are acidic when there's no oxygen in it. So we threw Lavoisier out the window. We don't care about that too much. We moved on to Davy, and Davy showed that Davy hypothesized that acids must contain hydrogen and bases react with acids to form salts. So in Davy's theory, everything that contained hydrogen was basically an acid. And that's why it was limited, because why did so many hydrogen containing compounds, why were they not acidic? Why was water neutral? Why was methane neutral? And that wasn't really explained until Arrhenius. So Arrhenius got it right on, proposing that acidity and alkalinity are due to behavior in water specifically, because that's correct. The way the acids and the bases react with water makes the hydronium and hydroxide, so that's right. And he said that acids dissociate to form hydrogen ions, bases dissociate to form hydroxide ions, and then what happens then is that they can react to form water and a salt. He also proposed that strong acids dissociate to a higher degree than weak acids. This is so correct. That's exactly what determines the strength of an acid. it's the degree of dissociation. So right on there, Arrhenius was probably the closest. And what really limited Arrhenius was that it only talked about behavior in water. So there are acid-base reactions that can happen in gases. There's like tons of different ways that acids and bases can react. It's not just limited to water. So since it only classifies aqueous substances, that's where it was limited. It also didn't explain the pH of salts. More on that later. But that led us to the current theory, I guess. We've had like an extension of this theory to do with electrons, but we don't really care about that as much as Brønsted-Lowry, because Brønsted-Lowry is what is in the syllabus. So an acid is a proton donor. By proton, we mean a hydrogen. So a H+, that is a proton. An acid is a proton donor. It donates a proton. So similar to Arrhenius, where it said it dissociates to form H+, kind of same idea. It donates the H+, which a base, the proton acceptor, accepts. And that's how acids and bases interact. So acid's a proton donor, base is a proton acceptor. How do I remember that? Acid has a D in it. D is the same as donor. D and donor, same thing. So acid is a proton donor, base is a proton acceptor. And it can only donate a proton if the base can accept it. So that's Brønsted-Lowry theory. And I love Brønsted-Lowry theory. I think it's the simplest thing to remember, because you just have to remember that one donates, one accepts, and then you can call it a day. So you have to keep in mind, obviously, like all the other theories that kind of led to that theory in the end, especially Arrhenius with talking about the strength of acids and things like the behavior in water specifically. All of that is still being taken into account in Brønsted-Lowry theory. It's just they all add on top of each other, if that makes sense. So yeah, I love Brønsted-Lowry theory, and yeah, that's good, because the second inquiry question is all about Brønsted-Lowry theory. So back to Brønsted-Lowry. Which of the following is not a Brønsted-Lowry reaction? For this, you just need to see if someone's donating a proton and if someone's accepting it. So if we look at B, you can see that they kind of just combine. No one really donates or accepts just an H. If we look at A, we see that NH4 donates a proton to NH2, and then they both become ammonia. We see here in C that the H is donated from here to be added on to here, so it becomes H2. And then same kind of idea at the bottom, we have an H from here being donated to here. So B is the only one where none of that's happening.